Hello everyone, welcome to the lecture 2 of ECE 573 Advanced Embedded Logic Design Winter 2022 semester. In this lecture, we are going to discuss about the hardware software co-design and bus protocol. Before we begin the lecture, I would like to reiterate the few things about the AELD course. Google Classroom code is given here. The lecture timings are Tuesday as well as Friday. The Friday lecture timing is still not confirmed. Hopefully, it will be confirmed by the academic department by next week. For the lab requirement, please install the Vivado with SDK software-defined kit 2019.1 version. We will upload the installation guide on the Google Classroom. Make sure you install in the next 2-3 days because it takes around 3 to 4 hours to install the Vivado. In case you don't have a laptop with at least 8 GB RAM, then you can use the lab desktop via remote connection. We will float the form on the Google Classroom. Please fill up the form. Again, how to access the FPGA on the SoC boards remotely, we will share the details or another handout in the couple of days so that you can use the boards in the live lab as well as to submit your homework. Regarding the evaluation, we have increased the lab marks to 15%. So every lab carries 1.5 marks. So there will be a 10 labs evaluation. And then the project component is 25% instead of the 30%. Labs and the project must be done in the group of 3 or 4 students. Viva will be taken as a group Viva, but anyone should be ready to answer the queries. So let's start with the discussion on the intelligent reconfigurable hardware software co-design. We have discussed a little bit about the hardware software co-design in our lecture 1, but we are going to revisit that details along with the need of reconfigurable and intelligent architectures. So as we have discussed, we are talking about the heterogeneous system on chip, where you have the different types of components. For example, you have the sequential processors, you may have the co-processors like DSP, SIMD, that is the single instruction multiple data, floating point unit coprocessor, you may have ASIC, you may have FPGA. So once you have your algorithm, which part of the algorithm to be implemented where, that is called as a hardware software co-design. Then, as we discussed in the previous lecture, there is a requirement of the flexible hardware, or it's a upgradable, like you should be able to upgrade it to the futuristic requirement. So this is called as a reconfigurable one. So what we mean by reconfigurable hardware, and then why we need an intelligent reconfigurable hardware, that we are going to discuss. So consider that you have been given the algorithm, which is fairly complex algorithm, and it consists of the multiple sub-blocks like F1, F2, F3, F4. Right now, I have just taken a simple example where you have the output of F1 is passed to the F2 and so on, but it may be such that the output of F2 may be used here, or output of F2 may be used here, or something. So that is there, but we don't need to worry about it. So the first goal is that I need to do the hardware software co-design. For example, if I consider the simple Zinc SoC which we are going to use in our lab, it has two parts. One is the PS, that is the programming system, and the PL, that is the programmable logic. So PS is nothing but the processing system, that is your sequential units, and the PL is the programmable logic, that is FPGA or ASIC. Now, which part of the algorithm to be put on which area, so that depends upon your user requirements, area, cost, power consumption, acceleration time or execution time, all those things. And based upon that, you need to find out. So the conventional way is that you implement everything on the processor and you use the profiling tools. So there are tools are available in the market which tells us which function or which function takes how much clock cycle. Then you will find out the function which takes the maximum clock cycle, and you can see that, okay, this function I can move to the hardware to accelerate it. But is that sufficient? No. That function should have some parallelism so that you can speed up on the hardware. If that function itself is a sequential, then you can't do much there. Okay. So one thing is that you need to profile your algorithm. You need to have the knowledge of your algorithm and see that which part of the algorithm can be parallelized so that it can be moved to the hardware. So this is the one thing. Second thing is that whenever you implement something on processor, your operation are limited to the word length of the processor. So if your processor is 32-bit, so all the ALU and everything will be in the 32-bit. So the advantage of sometimes that you can go to the FPGA or the ASIC, but then you can choose the word length of any size. You can have 1-bit, 2-bit, 7-bit, 12-bit, 18-bit. What is the advantage? You will get the desired accuracy as per and you will choose the word length accordingly, but then you will get the lower area utilization and your algorithm will be faster compared to your processor. So that is the flexibility we get. Third thing is, whenever you move something away from the processor, you need to understand that you are moving the task or load on the processor to some other task. That means your processor is less loaded and processor is free. So in any embedded system, you need to make sure that the processor is active, it responds to the emergency event in the real time. But if the processor is occupied with some other task, then it is very difficult for the processor to respond to the emergency event as quickly as possible. So by moving some tasks to some other co-processor, we are making the processor free. Okay, and that's where also the important part of the hardware software coding. So you need to decide which part of the hardware goes where. So this concept is applied to any algorithm, any signal processing, any wireless communication, any robotics, any machine learning, any deep learning. You have the nowadays you have the complex algorithm. You can divide the algorithms into the data path, control path. Control part you put it on processor, data path you put it on PL. But even in the data part, you can't move everything into the PL, right? You need to choose accordingly because you don't want to put everything on the PL and then spend additional cost for this PL. If in terms of the ASIC or FPGA, because both are costly, so you need to take your decision wisely. Sometimes it may happen that you want to use the PL. That is perfectly fine. So inside the PS also you will have SIMD processor, floating point processor, GPU. So in that also you need to take a decision. So basically by you will try out the different one. You make use of the tools, but tools are not that smart enough. But with the experience, I think you will be able to take the better decision. And depending upon the higher end, you may have the multiple co-processors and all, like real-time processor, GPU, ARM, FPGA, ASIC, and you can take the decision. And this is called the hardware software co-design. And this is what we are going to do in our AELD labs as well as lecture. But this is not it. Hardware software design is conventionally done for last 2 decades as well. So this is not something new, but the only thing is that as the designs become more and more complex, it takes a lot of experience. But as I told you before that now we need a flexible hardware or reconfigurable hardware or upgradable hardware. The conventional example is the say computer vision algorithm, where some models may work well in the morning or when daylight is good. Some model may work good in the night. So do you want to implement both the algorithms in parallel and choose the output of one of them, or you want the same hardware to be reconfigured with the algorithm 1 in the morning and algorithm 2 in the evening? So the second one is better because you take less area, less power consumption, because only one algorithm is active at a time, so less power consumption, and that's the advantage. So this is the advantage of the reconfigurable architecture. Also, it may happen that after you deliver it to the product to the customer, customer may say that, okay, now I want to upgrade it one more algorithm, say for the night time. So what you need to do, you just need to share the additional files, and instead of 2 algorithms, now your hardware can support the third algorithm. So this is called as the upgradability. And this is where FPGAs are getting more and more popular. What is FPGA? That is the field programmable gate array, while what is ASIC? That is the application specific integrated circuit. So application specific integrated circuits are designed for the specific algorithm, so they won't be able to support the reconfigurable features, while FPGAs are the one which can be field programmable. So even if you deliver your product to the customer, they can be field configurable. Also, suppose you have this much amount of the FPGA, and suppose you have the F1 here and you have the F2 here. Now, if you see here that F1 is fixed and F2 is you change between the can be changed between the two, F21, F22, F23, F24. But when you say, do you want to configure the entire FPGA together or only this part of the FPGA? So if you want to entire FPGA together, you need to change the, you can need to configure the entire FPGA via complete bit stream. But FPGA also support the another feature which is called as a dynamic partial reconfiguration. That means you need to provide the hardware file of only this part. So you will provide the 4 hardware files corresponds to 2.1, 2.2, 2.3, and 2.4, and only this part will get reconfigured. So this is called as a DPR. This is another unique feature of the DPR. What is the advantage of the DPR over the full reconfiguration? Your bit files are small, so it will take less memory, and the configuration speed is also less, because configuration time is also less, because you need to configure only small part of the hardware compared to the entire FPGA. So that is one is called that is the advantage of the FPGA. So with the reconfigurable features, now the hardware software co-design need to also consider that when you move something to the FPGA, you also need to see whether when you are moving that, can you exploit the reconfigurability? If not, then you should use the ASIC, and then the FPGA doesn't make a sense. So FPGA makes a sense only when there is a reconfigurability feature. If you are using FPGA for any algorithm where there is no reconfigurability, you are wasting a lot of money, as well as your area and power consumption will be higher than the ASIC. So when your algorithm is fixed, there is no requirement of upgradability, please use ASIC. When this is not a case, you can use the FPGA. So make sure that you choose the between the ASIC and FPGA carefully in your product. Okay, so when there is a reconfigurability requirement, FPGA will make a good choice. So what are the advantages of the reconfigurability? Power consumption is less, because now instead of having 4 algorithms in parallel working, you have only 1 algorithm working at a time. So your power consumption is less. So also you can move, your area requirement is less. So you can use the smaller FPGA or cheaper FPGA. And this will lead to your cost as well as the operation power consumption. So the cost requirement is will go down. This is not that you can support the future upgradation. So your product is rich in terms of the features, and it can be upgradable in the future. And in the today's fast changing technology, you need that feature upgradability. For example, in the 4G or 5G, you need a upgradability feature. But designing the reconfigurable architecture alone is not sufficient, because you can design the reconfigurable architecture, but how you will decide which algorithm to be used at what time? You have the 4 options for the F2. So which to be used at what time, how to decide? And that's where you need a intelligence inside your architecture. And this intelligence will sense your environment and then choose the algorithm accordingly. For example, in computer vision, that is true. Even in the wireless communication, based upon your wireless channel or the interference, adjacent interference, you can change your physical layer parameter like a transmission bandwidth, filter attenuation, modulation scheme, beamforming vectors. You can change them in the dynamic manner, and that is called as a intelligent reconfigurable architecture. Okay, So this kind of concept is widely there in the deep learning, wireless communication, and any other application. You will see that there is a need of the intelligent, reconfigurable hardware software co-design. So in the ALD, we will discuss mostly on the hardware software co-design. And in case you are interested in the intelligent reconfigurable hardware software co-design, then you can take up the IPIS or the capstone or the thesis project later to explore the these concepts. Okay, so now in the next lecture or next video, we will discuss about the bus protocol.